Okay. There are 3 websites. I'm still thinking if we need to build a PCB. I think it can probably. I'm not going to require everyone to build a PCB. If you like, I will let you do it. But I won't require that. So there are 3 links. Look at the links. The first one is a breadboard version. So the breadboard is something you can plug in to, and you don't have to solder anything. So it's a good start to test the circuit. So that's the breadboard at all the holes. And you plug in the chips onto the board and wire them up to the power supply. And here's a voltage regulator. And you'll learn how to design the voltage regulator on the PCB by yourself in 351. It's a CE 351 class. I'm going to teach next spring, but you probably won't be there. You need 2 prerequisites to take it, maybe 2023 spring. Okay. But if you want to take it, if you think you are smart, you have to take logic first. See when we are going to offer that logic class. Yeah, it's already too late. Have to wait until 2023. So that's a voltage regulator, and the battery supplies a 7.4 volts DC to this regulator, and it's being regulated to 5 volts. The reason we don't want to use 7.4 is it's just too fast. It's not giving the sensor enough time to think. Even though there's no brain, there's no CPU, it's not able to think at all, but it needs some time to respond mechanically to the wheels. And so using 5 volts is highly recommended to make it work. That's why we have to use this regulator to just bring it down to 5 volts. And here's an inverter chip. Because the digital logic signal is not desired, we need to invert it to make it work. Otherwise, it's going to return, not going forward. So we need to re-invert it and fit it into these infrared sensors. So the way this one works is, if you flip the car, you can see these 2 sensor modules. And if you are attending Circuit Engineering 201, you'll probably build a PCB, entire PCB of this car, and you understand what's going on for these IR sensors. There's a little component called comparator. I'm going to explain pretty soon. But now we just need to know that for every PCB module, these sensor modules, for each one, it has a transceiver pair. Transceiver means there's a transmitter and receiver. So it's a transceiver pair. So the dark one is a transmitter, and the clear one is a receiver. And if there's nothing in front of the pair, for example, like this, if there's nothing in front of it, then the transmitter is going to send this laser. It's a light signal. It's an infrared bandwidth, or it's an infrared wavelength over 740 nanometers. Do you know the visible spectrum? So the light can be visible or invisible. So the visible spectrum is between where to where? It's from 400 something nanometers to 700 something nanometers. That's the wavelength of the light. If it's longer than 740, somewhere around that, it's longer than 740, then it becomes invisible, and that part of the light is called infrared light. Usually the remote for the TV and remote for the car. I did a demonstration in the beginning of the semester. So they usually use IR signals or infrared signals. And for anything shorter, for the wavelengths, all the wavelengths shorter than 400, I think, 400 something, 480, 490. On the other part, these are UV lights. they are also invisible. You couldn't see them, but they are stronger energy. So these are invisible to the other sides, but in between 480 and 740, these are the rainbow colors, right? From blue to red. Okay. So here, the sensor signal here uses the infrared signal wavelengths. And so why do we want to use infrared, not visible, or not UV?
Infrared doesn't mess you up as badly.
That's one part of it, yeah. So it won't damage your eyes. But stronger ones will, but better than UV. Yes, but you couldn't see it since you can only see visible ones. That's why it's called visible, right? So you have visible lights everywhere, and if you have some sensors are working in a visible range, then it's always receiving signal from the environment. So a lot of noises. So infrared is better. And definitely you couldn't see it, but actually your camera usually can catch it. If you turn it on, you look at the infrared, not directly look at it because still some like laser beams, right? Just look at from the side. You actually couldn't see anything. It's transmitting our lights, but you couldn't see it. If you turn on camera or the phone, or your phone, you can actually see a little bit laser beam coming out from the transmitter. The reason is the camera has a light sensor, probably can sense that wavelength and display it on the monitor. So sometimes, if you do not know if for example, the car is not working, and you don't know what's going on, you don't know if the transmitter is working or not, you just use your phone to look at it. So you can see a laser beam coming out. So you know the transmitter is working, but it couldn't detect the receiver. So it's just receiving that signal and give a response to the car. So you have a pair of transmitter and receiver. And if you have nothing in there, then the transmitter is going to send a laser beam, but not being reflected back. There's nothing in the front. Or if there's a dark surface, then it's going to absorb that IR emission. Then still no reflection. So you need a relatively lighter surface. Can be white, can be gray, can be just light gray, like that, as a surface to reflect that IR light back to the receiver. So if you have a surface, this actually works. And I use the cardboard. I have a cardboard in my office. I'm gonna bring it over. And I use electric tape. It's a black tape to make a track on the board. But the board itself, the surface is light, white color, pretty light. So it's going to reflect the IR light pretty well. But the dark tape will not reflect enough IR light to trigger that receiver's response. So what's happening is if you have a tape track, a black track on the board, then you have two sensors. If you look at that one, you have two sensors. You just place the two pairs on the two sides of the tape. So the tape should be in the middle, right? So it's something like this. For example, here's a track, all right? Here's a track. And these are the two pairs, right? And whenever the car is out of the track, for example, is turning to this direction. So what's going to happen is there won't be any reflection because the black tape will absorb all these IR light signals. So there will be a difference regarding the received signal because it used to be white and white. So which means it's signal reflected, signal received. But whenever it's turning to that direction a little bit, so it's right above the black tape, the signal are gone. signals are gone because they're all absorbed by the tape. So what's going to happen is you design a circuit to, so for example, it's turning that direction, all right? And then what you want to do is turn off the wheel on this direction, but keep this on. So it's going to turn, it's going to correct the direction of the car because this wheel is off, but this is on. So it's going to roll in that direction to trying to make the turn. Vice versa for the other side. So if this one is going that direction, you want to keep this on, but turn off this wheel, so it is able to correct the direction of the car, right? Because the circuit can respond really quickly. So it's going to work like this. Vibrate a little bit, but always keep on the track. That's how that works. It's brilliant because there's no CPU on the car. It's just a very simple analog circuit, and it works pretty well. So I think they are. So that's the bottom line. You guys have to complete that part in order to get the full credit for the project for this class. And we have another one, the PCB version. A video tutorial from one of my students she worked on this 2 years ago in the summer. So here's a voltage regulator circuit. You have to design all these components in the PCB. The software's name is called Eagle PCB. So you draw these symbols and make the connections and convert it into PCB layouts. So circuit layouts like this. And then solder the components on the PCB. So you send it overseas, just China, right? And then it's $5 for 5 pieces. In 2 weeks, you have to get it done pretty fast, since we only have 4 weeks left, right? How many weeks left? 4. So there's a chance to get it done before we wrap up this semester. If you would like to do that, it's not required, okay? And I think so when she submitted the design 2 years ago, I just, ordered 20, 30, or 40, I forgot, pieces of PCBs. You design the PCB, you draw it, and you don't have to send it out for fabrication. If you want to do that, I can support you. I will pay for that. But if not, then I can still give you that copy, her copy, and give the components. You can solder the components to the PCB. But I think before do that, you should draw the PCB by yourself so you know what are these parts. Otherwise, you're just soldering the parts to the PCB. You don't know what are they. So you want to learn what are the parts first, including the voltage regulators, how to regulate the 7.4 volts to 5 volts, and how to solder the sockets on the PCB, and also a potentiometer, and also the IR. These are IR pairs, not the modules anymore. So they are the IR pairs. So you actually design the circuit by yourself instead of using the modules. And also solder a little surface mount LED, tiny LEDs. So when you're plugging in, you'll see this LED, you'll know it's turned on. So you can convert everything to a little PCB instead of wiring up everything on the breadboard. If you lost one wire, then you don't even know what is that wire. It's going to be super frustrating. You have to look through the source circuit to find out that wire. And sometimes the holes on the breadboard can be loose. So plugging, maybe the connection is not perfect. Then the voltage potential cannot be conducted to there. Then you don't even know what happened. very frustrating. So my experience is after the circuit is being demonstrated on the breadboard, convert it into a PCB as soon as you can if it's a comprehensive project. Like if a company asking you to design a system, you do want to do that. Do not keep everything on the breadboard for a long time. You know, if you put it in the corner, probably it's going to still work, but sometimes people will just unplug some wires from your board. You don't even know why. They probably just want to borrow one wire from the board, and it takes you another 2 weeks to debug it. So just try to convert it to PCB. But you do not want to directly go to the PCB join because you don't even know if that works. If you draw the PCB, you print it out, you cannot change the traces. They're already printed on the board. If there's something wrong with the design, then you have to redraw it. So that's why you have to demonstrate everything on the breadboard first, and then convert everything to the PCB. So the first one, so this one works in this way, and the other one works in a similar way. Pretty noisy. That's doable. If you want to do more, let me know, okay? So we can do the PCB version. And after you take logic, after you take my controllers, I have more projects to let you guys to work on, if you like. I have a lot of stuff I want to hire people to work on. And PCB version, you know, same function, same circuit, just on a different platform. Okay, so that's not required. If you don't want to make a PCB out of it, how to make a PCB? I have these 4 tutorials. Just follow. Take you probably just since you have learned voltage and current, right? You understand voltage and stuff. So you should be able to do that. Just draw them, starting from a very simple PCB drawing. Just to complete the 4 tutorials probably will take you a week or less. Depends on how much time you put on that. So go through the tutorial first and come back to design your own PCB. So there are 3 options, right? First, do everything on the breadboard, demonstrate it on the track, done. You get a full credit, pass the class, okay? And second option, demonstrate everything on the breadboard, go through the PCB tutorials and draw the PCB, and solder the parts on the PCB I'm going to give to you. So from my TA who created all the tutorials. Fine. So you can still practice the soldering and also the PCB drawing as well. And the third option, the ultimate option, so demonstrate everything on breadboard, do as soon as you can, probably next week. I give you the parts and get it done next week, just in 2 hours. It's very possible. And then go back home and start following the PCB tutorials. Draw the PCB and send the Gerber files. Gerber files are the PCB drawing files, design files. Send it to me. I'm going to send it to China for fabrication. You will receive it in 2 weeks. And you can solder the parts to your own PCBs and you can own it for free. Give it to you. Okay. That's your call, right? Whatever you want to do, let me know. However, just remember, keep in mind the bottom line. If you want to get a good grade from this class, make it work on the breadboard first. All right. So let's see how that works. So come back to the breadboard version. Because we're not even designing the sensor module. So it's very simple, actually. I'm pretty sure 50% or less, or even more of the class next week will get it done on the breadboard. So that's a driver. You need a motor driver. And the way it just follow the connections. So see how you want to connect which pin to where. Okay. So the DC motor the DC motors, you have two wheels. Actually, I have a lot of parts. Very simple. Wheels, motors, and every single motor has two wires, and you know, voltages are relative, right? You can connect the short area to here, plus minus. Then the motor is going to rotate in one direction, and you swap it to rotate in another direction. And that's it. Our DC motors apply voltage, it's going to start rotating. That's it. So these are the connections of the wires from the motors. 1, 2, that's for one motor on one side. And here's another motor on the other side. And that's the ground symbol. You just shorting these two and ground it. That's a connection. Just follow the connections. Here's a motor driver. The reason I can tell is because one motor, another motor. Right? Just follow the traces. See which wire should be connected where. Okay. And that's an inverter because the IR modules need a signal to be inverted. So 1, 2, 3, 4. These 4 pins are being shorted to ground. So they are 0 volts. And this is a voltage high or power supply. And this is also power supply. And power supply, power supply. See how easy it is, right? Just make these connections. And these are the inputs to the driver, or you can say they are the outputs from the inverter. The IR signal, the IR sensor will send on or off. So the signal output from the IR sensors are either the VCC or ground. So these ones are being sent to the inverter and being inverted, and then connect to the driver to turn on and turn off the motors. So the way that works is, remember the sensor is out of track, then there will be a signal difference. And that signal, that response need to be sent to the driver to control the on and off of the motor. Okay, and eventually just build this one on the board and test it. Any questions? Is it too boring? If you like, yeah. Okay, so I think the circuit is simple, but practicing on PCB drawing is really rewarding. There are many companies that are hiring people who knows how to design PCBs. So starting with a simple circuit and run through the whole process, the workflow from very beginning, like demonstrating the circuit functionality on the breadboard, and then convert everything to the PCB drawing and send it out fabrication and receive it and solder the parts of the PCB and demonstrate it. That's the whole workflow. Can give you a lot of experience regarding designing circuit boards in the future. Not too many, programs are allowing students to build a PCB in the first year. It's very unique. And for some of the undergraduates, they probably won't be able to get one PCB before, until their fourth year in the college, where it's very possible like they have zero PCBs during the 4 years. It's not required. They just demonstrate everything on the breadboard and they're done. Just read lab report and get a grade and graduate. The reason I think you guys should make as many PCBs as you can is because I didn't make that many PCBs in my undergraduate, and I hate it. I think that's totally wrong. They should let us use whatever the pros use in the industry, like making PCBs, programming microcontrollers, not using assembly language, but using C or C++. Please. Damn it. This is just like if you not just when I was in college, but also the other institutions I attended in the US. They just follow whatever their professor, 20, 30 years ago, even though they are new professors. They just follow keep thinking about that's what this class should be because I was taught in that way. And they just teach them assembly. So start programming a microcontroller and start moving the values in between registers, but not understanding why, because it's not really readable. And getting frustrated in the first week and drop out. What's the point of that? I mean, so the worst time or the worst experience in my college was the time when I was taking microcontrollers and the teacher told us to program in assembly. That's the worst time in my college life. But you know what? Microcontrollers are the most important components you want to learn because they are super useful with controlling pretty much everything. Like these ones, robots, TVs, everywhere. And why not just start from C++? Why assembly? I think that's a crime. I mean, why all the people are doing that? So that's why we just use C++. I mean, I developed 20 projects, tutorials online. If you go to my website, so start from here. You can see we have a lot of projects, but I divided the class into two groups. There's one. So the ESP32 project is, I think, it's a little bit difficult, but it's really worth to do it since this is directly a project from the company who sponsored my lab. And I just make it a simplified version and used it in my class. I'm kind of lazy because I don't want to develop a new tutorial for you guys. I did it, I sold it, I just converted it into a simplified version and let you guys, work on it. I think it's useful because all the concerns when you are doing something in real world is useful. It's not just everything from the textbook. You will never find out like something like this in any textbooks. They'll just let you programming assembly. And it's very long. If you look at here, it's not moving really significantly. So that's gyroscope and accelerometer sensor, and being connected to a ESP32. It's a 32-bit microcontroller, has 2 cores, and you can also use a free RTOS. It's a free real-time operating system, so you can schedule different tasks at the same time. It's not a simple Arduino. You just code it from top to bottom, just saying repeat that loop, or repeat all the tasks inside the loop. Here is different. You schedule everything in different pipelines, and they will just do part of that task during every time frame, and then stop doing it, and then let another task to do that task, part of that task, during another next time frame. So just keep doing that, and then whenever the last task is done, then come back to the first task and keep doing the one which is not completed yet. That's how you program an advanced system, a microcontroller system, to control some difficult tasks instead of just very simple, like blinking LED or something. So if you search for RTOS engineers online right now, if you just search in Google or embedded systems, RTOS engineers, the starting salary is over 150 everywhere, and job opportunities are everywhere. But if you search for like Arduino engineers, probably no, it's too simple. It's a high school level. But we'll do a lot of Arduino programming as an entry-level project. But you want to learn how to make PCBs, how to interface microcontrollers with SD cards, so you can detect the signal and save it to SD cards, and send it to a data center wirelessly, and save it over there, and then you can grab that microcontroller or the SD card from the data center and load it into the computer and do analysis for the data. So these are, so that's a tutorial in detail, and it has a part 2. So after everything is demonstrated on the breadboard, we should convert it into a PCB, and so I'm just showing you guys how to find out how to down select the components for the voltage regulator on the PCB. So you have so many options. So why this one is fine, why this one is not working, things like that. And keep going. So these parts are, some of the regulators are tiny. For this one, it's super small. I think it's probably 2 millimeter by 2 millimeter or something. And it's a surface mount component, which means the pins are at the bottom of the chip. You cannot actually access to, when you are soldering it, you cannot heat it up. You have to use an air blower, like hot air blower, to blow it. I have 5 in my lab, so it's rare, I can tell you. When I was in ULV, University of Nevada, Las Vegas, they have 0. You'll see everyone, some electric labs, they don't have anything like that as well. It's just super hands-on, super engineering. Research is great, yeah, but sometimes we want to really build some hands-on projects. The professors in bigger institutions, they don't like it because it's not getting them money. Since we don't have graduate students, we don't have undergraduates, I hope you guys can experience this at least. Research is great, right? Research is great. But before you get into that point, can we just learn whatever is very practical first? Okay. Doesn't like all the other students are doing research right now. They are senior students doing research. It seems like they skipped all these hands-on projects directly doing the research. It's not making sense to me. Okay, that's the final PCB for the system. It has a wireless module, has a gyroscope and accelerometer in the middle. So that's a voltage regulator, and with all the capacitors and resistors. It's been powered up by a little LiPo battery, rechargeable, 3.7 volts. And I think there are many other projects. And there's another project I did for Pagosa Springs 2 years ago, I guess. I think that's this one. Yeah. So So what they want to do is they just want to update the temperature of the tubs automatically instead of just letting their people to test it and change the number manually, the temperature manually for each tub. They have 24 tubs. And so how to do that? 24, yeah, sensors. 24 tubs on the resort. It's a pretty big resort, have a hotel. Have you ever been there? Pagosa Springs is a Pagosa Springs Resort. That's the name, the name of it. Hot Springs Resort or something like that. Yeah, I've been there. So it has a hotel. It's a pretty big property. Have 24 tubs, and all the tubs are natural tubs, so they don't have the electrical lines running underneath it. So you need temperature sensors, but they have to be waterproof. First, second, the water is not the regular water. The water is acidic. It's corrosive, actually. Not corrosive to you immediately, but it's corrosive to the sensor. I have to find out the sensor which is resistant to the materials, mineral materials in the tub, in the water. Third, how do you make a network out of it? So you don't want every single sensor to be an individual sensor on the property. How to pair them up? And yeah, how to monitor the temperature. So first, still, how do you pair it up? Power. Voltages, right? As voltages, batteries. Batteries. You have to pay a person $50,000 a year to replace the batteries every month. Is that reasonable? No. So I was thinking, it's an open topic. I'm not telling you my design is perfect, right? Let's just think about it. This is a project for like your family business, right? This is your property. I do need 24 sensors to form a network. So I don't have to hire a person for $50,000 to replace the battery and monitor temperature and change the temperature on the sign. How do you pair it up? So temperature sensors are everywhere. So if you follow my tutorials, I probably have included every single popular temperature sensor on this market. Start from thermistors. It's a little resistor, but it changes resistance when temperature changes. So you can monitor the voltage drop between the resistors because the temperature changes, the resistance changes, right? $1 I can buy 100 for you. No surprise. Cheap. Digital temperature sensors, I have at least 5 different types of digital temperature sensors. And thermocouples, I don't actually use it, but if you take Engineering 271, it's one of the labs. You have to, use thermocouples to do it, but it's just too big. As a computer engineering person, I don't do that. Thermocouples is very common, but I don't use it. There are so many other good options. So the BMP 280, 380 temperature sensors can monitor temperature, humidity, altitude, pressure. It's a little chip and do all these things. And there's another one called HT, I forgot the name. So can do temperature and humidity at the same time. Very cheap, dirt cheap sensors. And not every temperature system can be used in this environment. Remember, corrosive, waterproof, low power consumption, things like that. So I found out there's only one temperature sensor is being wrapped in a tube, and that sensor is being placed in the tip of that tube. It's being sealed and has a long wire. So you place that probe into the water, and the wire can be connected to a little computer or microcontroller somewhere else. So you don't have to place everything close by the tub because you have customers, you have water there. Instead, so it's not damaging your circuit, right? So yeah, we got a sensor. Okay, so the sensor is done. So what about power? Power is pretty tricky because battery is definitely not a feasible option. You don't want to replace batteries. You have to dig a hole to take it out and replace the battery every month. So definitely not. Have to wire it up, yes. So they have all these road lights, the street lights on their property. So they do have AC power lines. So they can probably just got some AC power from these lights underground and connect to somewhere close by to the tubs. So AC, it's 110 volts. It's pretty scary. 110 volts AC power, like these ones, right, from outlet. And you have to use adapter, like the adapter from my laptop, right? The adapter, so you can convert that one AC to 20 volts. So you are getting a 20 volts DC, and 20 volts DC has to be regulated, or you have to, reduce that voltage to a lower DC voltage. That's why when you guys are building your circuit, you will experience the first regulator you are going to use. These ones to regulate whatever here in the input to 5 volts. So step down the voltage to 5 volts. So get that 5 volts, have a ground line, and you can put your circuits in here. Okay. So finally, how you can form a network so people can monitor the temperature. You use the wireless modules. So what we used is ESP8266, that Wi-Fi module. The reason I want to use a Wi-Fi module is because on their properties, they have Wi-Fi signal covered on that property. So we can utilize that Wi-Fi coverage. But other ones are not really reliable. For example, you want to use 2.4 gigahertz wireless modules. It's difficult to, because it's the same frequency, and you have sensors here, they can get confused. They don't even know like where the signal come from. The Wi-Fi is different. If you connect the Wi-Fi to that router, it actually knows the IP address of your transmitter. So definitely Wi-Fi is the option, right? So temperature sensor collected, send it to anywhere through the Wi-Fi module, and you can design a little software, have a GUI, it's a graphical user interface, which can collect all these data from that Wi-Fi modules, from the 24 Wi-Fi modules, to one software interface. So you can show all these temperatures and update the temperatures by itself. All right? So you can tell what's the temperature of each tub. Yeah, that project was done as well, and it's part of the 351 class. It's a 2 weeks or 3 weeks project for that class. You guys are like, snacks, please. Just stop. All right. Any questions on anything? No? All right, let's do it.